couple problems from Beer Johnson. You can see that we have this mass. Oops, come back here. This mass and a spring and a forcing function applied onto the thing. We don't see a damper, so this is an undamped force vibration problem. I didn't have many to choose from, so this is one that I had. So there you go. So anyway, let's see. The mass is equal to 4 kilograms. The spring constant is 450 newtons per meter, and isn't that metric nice? You don't have to play around with units. And see, the PM is going to be 13 newtons, and we want to find the amplitude. All right, so in part A of this, which says omega F is equal to 5 radians per second. Okay, so let's do some calculating. We can find the omega n like right away. So let's get him up at the top with the K over M. And you've done this a bunch of times, so I'm not going to fill in the numbers for you. We have 10.61 radians per second. So in this first part of this problem, we have an R of omega F over omega N, and we can find quickly, yeah, that's going to be 0.4714. So one version of this, let's go capital X, is going to be our PM, as they're calling it, divided by K, divided by 1 minus R squared. And if you're having trouble with remembering that, we do have one right here as a magnification factor. Right, and of course, right here is another version of the thing, like that right there. Or you could go to the force damped version right here and just cross out that, and notably the square root goes away with that square, and we end up with the same thing. I'm just mentioning where I'm coming from. I hope you don't hear my stomach. I don't know why it's making noises. So we have 13 divided by 450 and divided by 1 minus 0.4714 squared. And we end up with a positive value, which is kind of expected because we're less than 1 right here. So we're on the left-hand side of, let's see, we got right this guy right here, right? We're somewhere here, right? So we're in phase. This is the in phase. Here's the out of phase when it comes to the undamped version of this. And so let's see what we get for a value. I guess I'll just change to millimeters right away. 37.14 millimeters, and we're in phase. And that agrees with the back of the book. Then we go to B. And now we're going to have omega F is equal to 10 radians per second. So our R is going to be 10 over 10.61. Is that true? I'm trying to think right here. Yeah, it's still true, but it's going to be, so I was thinking that was going to be the out of phase, but actually you can just see right from there it's going to be in phase, right? But this gets really close, 0.9425. So we can expect, coming back to this, that it's going to be really high right there. The magnification factor is going to be large. And we could just stick the numbers back into there. So it's the same numbers. same equation. So we go 13 over 450. This time is going to be 1 minus 0.9425 squared. And that is 258.7 millimeters, but still in phase. Okay, so now we shift over to the next. Oh, and by the way, that was the same here, 260. All right, close enough. Now we go to the next problem right here. And we have almost the same things. We have a different, okay, so we have okay, so we have this 4 kilograms. We have a different magnitude here. So M is equal to 4 kilograms. PM is now equal to 9 newtons. Omega F is equal to 5 radians per second. And now we don't have an amplitude, right? Right here. That is going to be, so the amplitude we want, the desired amplitude, is 150 millimeters. And so we want to have in phase of the applied force and out of phase of the applied force. So what that really means is when we go to try to take this apart. So there's a couple different formulas sometimes for, we used this guy right here, that one right here. But that's, we took a lot of things apart. So let's see, do I have that formula written out differently? We got this one. Still could use a little bit of help right in there in terms of the math, but we have a different version of that. Let's see if we know. No, these are all this is our first forced one right in there. So I could look this up or I could try to figure it out. Let's try to figure it out. Why not? Okay. So not the best time to try to do that because it's really late at night. But we have this X is equal to PM over K times 1 minus, let's go this, omega F squared over omega N squared. Now, we can multiply the top and the bottom by K. So we just go, okay, so let me write that down. K and K. And we could also replace, let's go the other direction. We're going to replace 1 over omega N squared is going to be equal to M over K, right? So when we go and distribute this K here, we get K minus, and then the K is going to get rid of this K right here and just leave an M times omega F squared. Did I do that right? Yep, I got it right. Yay. So using that one's going to make it a little bit easier than the previous one because we isolated K. And that's what we're trying to find. We're trying to find the spring constant, determine the spring constant. So let's see where we're going to switch to. Let's go to bolder blue. Let's go to baby blue. Baby blue. All right, cool. And so we go, so writing this out, 0.150 is going to be equal to, and we get 9 newtons on the top. You have a K right here. It's going to be minus M 4 times 5 squared, right? So manipulating, putting that out to the side, I'm going to go 0.150 times K. All right, so we have 2 choices right here. So let's go ahead and put that guy in there. All right, so that means that's plus or minus. Let's do the plus version right now. So that's what I started to do. And so we're going to go minus 0.15 times 4 times 5 squared is equal to 9, right? And if we solve for that, we're going to have a lot of stuff on the right-hand side. Let's see if I'm going to, no, I got to add, I'm going to add that on, right? So I'm going to go 0.15 times 4 times 25. You're going to add it with 9, and then I'm going to divide by 0.15. And I get 160. And you could say that this is the in phase one. Well, how do you know that? Well, you could also find out what the natural frequency is going to be. So the natural frequency is going to be 160 divided by 4, right? So you had 160 divided by 4, take the square root, you're going to get 6.3, did I do that right? 6.325 radians per second. And so then when you go to find the R for this, you're going to have omega F over omega N, yep. And so that's going to be 5 over 6.325. So you get pretty much 0.8, 0.7906. And because that's less than 1, that's on the left-hand side, and therefore it's in phase. So we got it correct in both accounts. The other way that we can approach this, let's see, deep red. We could now, okay, so this was like a positive denominator. So we go to the negative denominator, and we would get negative 0.150 K, and then plus 0.150 times 4 times 5 squared equals 9. Okay, so what we're going to subtract that 0.15 times 4 times 25, but subtract it from 9 minus, you get a minus of, no, yeah, you get a minus value. I think we get close to minus value. Why didn't that work? Okay, yeah, you get it. Okay, yeah, so we get a 9, and then of course it's negative, so it cancels out, and then 0.15 divided by it, and you end up with a K that is going to be 40 newtons per meter, which agrees with this, and our natural frequency is going to be 40 divided by 4, should be the square root of 10, or 3.162 radians per second, and therefore the R is going to be 5 over 3.162, which is 1.581, greater than 1, and therefore on the other side, and therefore of the of resonance, and therefore out of phase, right? And just to go back to this guy right here, we had one that was like over here somewhere, so where they're in phase, and we had one over here somewhere, and so we were out of phase. And it's late at night, so I'm going to bed. But anyway, I hope that was educational about phases.